Did I turn it off when I clicked on it?
I don't know.
I think I did. Yep, it was on for 6 minutes. Okay. There'll be a part 1 and a part 2. Okay. So, saying it again, here's a few different ion compounds. If I took barium sulfate and put it in water, it's a chunk of barium sulfate. It is soluble, and this is what it means by soluble. The ions come apart and they're just floating around. All right. Insoluble. That's the exception. I need something that's insoluble. Sulfide. Barium sulfide, not sulfate. If I did that right, that's insoluble. So barium sulfate is soluble. Barium sulfide, I'm going to keep doing that. Aluminum sulfide is not soluble. If you put aluminum sulfide, what happens is it just floats down to the bottom and sits on the bottom. The chunk of it will just go down to the bottom and sit there. That's kind of the natural way to think of solubility. You put it in water, it dissolves. And when it dissolves into ions. It just kind of disappears from your view. If it's insoluble, it's just going to hit the water and then sink down to the bottom. That's one way to think of solubility. For the discussion today, it's helpful to realize that if I did have these, saying it this other way helps you realize that you can still have these ions in water. They just came from a different source that was soluble. What that means is, since this is insoluble, the other way to think of insoluble is, insoluble means if these ions bump into each other in the water, they will stick to each other. What I mean is their natural state in water is to be together if they're insoluble. So these ions, as they float around and start bumping into each other, I guess a couple of these and 3 of these have to bump into each other. But once they do, they will form and they will gather up into a big chunk. It won't take too long because molecules and ions and atoms, even if it's just a beaker sitting there on the counter, everything is moving. So eventually all those ALs and S's will come together and form Al2S3 and land on the bottom. Whereas something that's insoluble making this too neat, these should be jumbled a little. NaCl's natural state in water is to be apart as ions. So when these two bump into each other, they just bounce off of each other. They remain ions in the water. 2 different ways to think of solubility. What I think is the superior way to think of it is, say it this way, something that's soluble in water, its natural state in water is to be apart as ions. Something that's insoluble in water, its natural state is to be together in water. Solubility and this solubility chart that I've got summarized over here. Let me pull out some examples. So I'll pull this from question 48. Ignore for 47, C, and for 48, B. This is from 48. How do you use this chart? This is barium and sulfur. So you're looking for barium or sulfur in this first column. We find sulfur here, and it says anything with sulfur in it is insoluble, except for these. The exceptions are NH4 is one of those polyatomic ions, so I have to put a 2 there. So ammonium sulfide, I might have said sulfate again, I'm going to keep doing that. First column here, one of those charts says alkali metals. This first column is the alkali metals. The second column is the alkaline earth metals. I'm just calling it first column and second column. But it's saying the exception here where it says first column means any of those. So H. H2S, Li2S, K2S. And also these three here, calcium, strontium, and barium, that shows up again down here. That's the second column, that's these. So those would be CAS, that's RS, EAS. What I've just done is written down all the exceptions to this. So something that is sulfide will always be insoluble except for these. These are soluble. Those are the exceptions. The key here is this column is saying these are always soluble or insoluble unless this. You follow that? That's the information in that chart. The top one is just the opposite. It's saying everything that has NO3 in it is soluble, and there are no exceptions to that. Anything nitrate, and this is acetate. Is that acetate ion mentioned over there? So anything NO3 and anything acetate, there are no exceptions. They're always soluble. And here's chloride, bromide, and iodine, these three. And these are the exceptions, meaning AgCl, AgBr, the H2, that's a polyatomic ion, that's called mercuric. But it's a 2+, so I'm going to have to go Hg2, Cl2, Hg2, Br2. Because that's a polyatomic ion, I think we always put the 2's there. What else? That these are the exceptions here. What this is saying is anything with chloride in it is soluble, except for these. Anything with bromide is soluble, except for these. These are insoluble. Do you see what I'm saying? Okay, that's how you use that chart. So the examples I have BAS, here's S. BA is over here. So it's insoluble unless this, so this is soluble. Na2S, Na is in the first column here. So it's one of the exceptions, so this is soluble. Calcium nitrate, everything nitrate is soluble. SO4 is here. Everything sulfate is soluble except for these. And that's one of the exceptions, strontium. So this is insoluble. Al2, okay, so everything sulfide is insoluble except for these. And this one is, aluminum is not in the exceptions. So this is insoluble. You following this? K2SO4, is that soluble or not? It's got SO4 and it's got K. So you find your SO4 here. Is K2SO4 soluble? Is it? Sorry. Good. K2CO3. You find your CO3 here. Is that soluble?
Yes.
It's soluble because K is in the first column. PbI2, I is here, Pb is in the exceptions. So PbI2, soluble or insoluble? Insoluble. Nickel carbonate. Carbonate. It's insoluble except when there's NH4, which is ammonium.
Oh, it's insoluble.
So it remains as an insoluble. CH3OH, here's your OH. Yeah, I probably should have dropped that one out too, an exception. But that's how you figure out what's soluble and insoluble, and that is a skill you need to have because this next section over precipitation reactions is where we're going. And to be able to work with precipitation reactions, you need to know what's soluble and what's insoluble. That example where I showed the ions in the water, and I said, but hey, this is insoluble, and they come together. Once they come together, they'll just float down to the bottom. That stuff at the bottom is what's called the precipitate. You hear weathermen say, we're going to have precipitation today. That just means something falling down, precipitation. So the idea that it goes down to the bottom and sits on the bottom, that's what we mean. That's why we use the word precipitate, because it falls down out of the solution and goes down to the bottom. Okay, I'll leave the solubility rules there. We have talked about reactions, but we basically just did, I include reactions in test 1 just for the math, because I cover so much of the math for test 1, I just throw in the stoichiometry stuff, calculations. But now we'll talk a little more in detail, specifically precipitation reactions. So here's a reaction. Potassium iodide. First I'm going to do this. You might get a question like this. Those that I had for 53 and 54 look like this. You put this and this into a beaker of water. And then the question is, what happens? The first thing you need to figure out is, If they don't come apart as ions, no reaction is going to occur. Meaning, if you put Ki in, here's I, K is not an exception. That is soluble, and because it's soluble, I'm going to put AQ here. Aqueous, meaning water. Because it's soluble. This means it's soluble in water. PbNO3, all nitrates are soluble. So that will dissolve. Meaning we'll have K plus ions, I minus ions, Pb2 plus, NO3 minus. All those ions will be in the water floating around as ions. That's what we just figured out. Now that we have that condition, that is both are soluble, now this can happen. K can float around in the water and bump into I, but they're going to bounce away because its natural state in water is to be apart as ions. K's probably not going to bump into Pb because they're both positive, so they're not even attracted to each other. So they will repel each other. K and NO, those will be attracted to each other. But when K and NO come together, so basically what you do to write over on that side is you take this positive ion and stick it to this negative ion. You take this positive ion and stick it to this negative ion. Meaning I can go ahead and write this. I can write, that's a negative charge, that's a positive charge, so there's no stoichiometry over here. And then these come together, which we write as, and now you have to ask yourself, is KNO3 soluble?
Yes.
Everything NO3 is soluble. That's aqueous, because if K and I bump into each other, they just bounce away because their natural state is to be ions. When K and NO3 bump into each other, they bounce away because their natural state in the water is to be ions. When I and Pb bump into each other, it's insoluble, so they will form S, solid. So what we just determined is this is the precipitate. Meaning if you put this and this in a beaker of water, you're not going to see these ions anymore. They're still going to be dissolved in the water, but you'll see a solid form and it'll float down to the bottom. Then you can filter it out and isolate it. That's why this is called a precipitation. Sort of the point of a precipitation reaction is to get the precipitate, meaning you're going to filter this, dry it out, and save it and use it for something else because you needed yourself some lead iodide, lead-2 iodide. So you go do this reaction, you get some lead-2 iodide. Notice if this was also soluble, you would put those two things in the water and then nothing would happen and you wouldn't have anything. You'd have some ions in water, but you couldn't do anything with them. They're kind of useless. So the whole point of doing these ionic reactions is to be able to separate these two things at the end. Oh, there is a little bit of balancing to do here. Some of these you'll have to balance. There's 2 Ks, and there's 2 Is, and there's 2 NO3s. I think that's all I have to do. There's only 1 lead. So now it's balanced. Before I look at the solubility chart, I can go ahead and swap the ions. These are all +1 and -1, so I'm going to have KCl, positive ion, negative ion, positive ion, negative ion. There's no stoichiometry to worry about here. So everything is 1-to-1. That's the precipitate. All right, now let's look at it. Is Ki soluble? There's I. It's not in the exception, so this is soluble, aqueous. NaCl. Cl, Na is not over here, so that's aqueous. KCl is aqueous. And NaI is aqueous. What you would say here is a reaction is when bonds break and then new bonds form. Here, bonds broke, we got K plus, I negative, Na plus, and Cl negative down in that water. But no new bonds form because the natural state of KCl is ions in water. And the natural state of sodium iodide is ions in water. So we call that no reaction. You would also get no reaction if one or both of these is insoluble, because you never get those ions split out, so no new bonds form. These ionic bonds break, but no new ionic bonds form, so you would say no reaction. So at minimum, you need these two both to be soluble and one soluble and one insoluble over here. That's the condition you need to have a reaction, to get a precipitate. Any other situation and you will not have a reaction occur. If one of these is insoluble or both are insoluble, no reaction occurs. If both of these are soluble, no reaction occurs. I suppose if they are both soluble, you can say a reaction occurred, but you don't tend to get examples like that. So this is the precipitate, this, no reaction. You with me? So what's going to be over here? Those two and those two. So it's going to be KCl plus. We know the charge on the nickel because the charge on chlorine, it's 2 negative, so the nickel, this has to be nickel 2. CO3 is 2 negative. It's on the polyatomic chart. But this K2 should tell you that that's 2 negative. So that's why I wrote this way. And I guess there's no, yeah, there has to be a 2 here. There's 2 CLs and 2 Ks, so I have to put a 2 there, so I have 2 of each on the side.
Do you want us to like balance them?
You're going to have to balance these. This is the only place in this class that you'll be balancing. I could put a quiz up that just has balancing in it, because I didn't really go over that with y'all. But I will do that when I get a quiz up. But now the question is, KCO3, so reaction or no reaction? K2CO3. K2CO3. Anything with CO3 is insoluble, except for these, and K is in the first column. So this one is soluble. Anything chloride is soluble except for these. That's not one of the exceptions. So far, we're thinking we might actually have a reaction. KCl, that's soluble. What about this? Is this soluble? Nickel carbonate, is that soluble? Everything carbonate is insoluble except for these, and nickel is not in the exceptions. It's a solid. Yes. So do we have a reaction? We do have a reaction. And that's going to be our precipitate. Just do this one. K2CO3, that is soluble. And this is soluble. Almost wrote soluble. So far, it's possible that we have a reaction. Now what goes over here? K what? KNO3. Positive ion, negative ion. Positive ion, negative ion. We want this positive ion to go with this negative ion. NO3 is one negative, K is one positive, so I'll leave it like that. Since there's two of these and two of these, I need to put a 2 here. That's balancing the reaction. There's only one lead and there's only one CO3. What's the charge on lead? If the charge on NO3 is 1 negative, what's the charge on lead? Yep, there's 2 of those negative charges. So lead is 2, and CO3 is 2 positive, so this will just be like that. And there's only one of these and there's only one of these, so that's balanced. All right, KNO3, that's soluble. Everything carbonate is insoluble except for these. So this is soluble. That's our precipitate. Gotta be some of these. K2SO4 is soluble. AQ.
Wait, Doctor, could you explain how the PVC affects the insolubility?
Why is this insoluble? This header here says anything with these in it is insoluble, except for these.
Oh,
You got it? K2SO4 is soluble. Anything with I in it is soluble except for these, and strontium is not in the exception, so this is soluble. So far, we're good. I hope there's some of these, but. All right. So what goes over here? K what? Yep, Ki. Positive, negative, positive, negative. We take this positive and put it with this negative, Ki. I is 1 negative, K is 1 positive, so we write it like that. There's no number here, there's no number here. But there's 2 of these and 2 of these, so I need a 2 here. Okay, now we have SR and SO4. Those are both two valent, so SR. Okay, Ki, that's soluble, so aqueous. SR, SO4. This is soluble. So
It
with
has
this,
SR, so it's solid.
it is. So that's our precipitate. So far, we haven't run into a no reaction. Got these examples from the exercises. Just do it the way I said to do it. I'll probably have to come up with, use those as a guide, but, or use these as a guide. But it looks like all of those, at least all of them we've looked at so far, 51, 52, 53, and 54. If no reaction occurs, write no reaction. So far, every one of the examples I did, I will, when I make quizzes for these online, I will have some of them where they're both soluble. So you'll have an opportunity to say no reaction. Okay. Precipitation reactions. Exercises for this. Say again.
Next to ionic. What's
Up
it?
here,
What is EGN?
equation. So molecular equation, I'm going to rewrite these little things over here.
Okay.
But, so starting with the molecular equation. All right. That's called the molecular equation. It's kind of a misnomer because those aren't molecules. I don't control the nomenclature in chemistry, but these are all ionic compounds. It's covalent compounds that we call molecules, but we call that the molecular equation, I guess for lack of a better word. Here's the ionic equation. What you do is you take all of these and you split them out into their ions. You see that there's a 2 there for the K. So there's 2 K pluses. And then we've got plus 2 minus plus And I'm gonna do the same thing on the other side, sort of. And we still do this. It's kind of superfluous, but folks like to do this. I mean, if it's an ion, it's aqueous. It's dissolved. Okay, there's half of the ionic equation. You see what I'm doing? I'm just splitting things out into their ions, and I'm making sure I'm keeping the number of things that are there along with it. Okay. So here I've got 2K plus aqueous, and I've got plus NO3 aqueous, 2K, and I have 2 Ks here because of that 2, and because that 2 is on this molecule. That 2KNO3 is just saying there's 2 of those. So I have 2 Ks, and I also have 2 NO3s. And this should balance 2 NO3s, 2K plus. We don't have Pb2 plus and CO3 2 plus because it's solid. We have that. So this is sort of the key here. I don't write these as ions because they aren't ions. They're ions on this side, but not on that side. Because when Pb and CO3 found each other in the water, they stick. And then more PbCO3 starts sticking to it. It starts doing this. I left the charges off, but it starts building a crystal. See what I'm saying? Because this is what ionic compounds are. They're always this crystal lattice structure. So this starts to form in the water. I should have charges on here. Keep going. The net ionic equation, you're basically crossing off everything that's the same on both sides. Meaning we have 2K plus on this side, we have 2K plus on this side. We don't have a CO3 2 minus over there, and we don't have a Pb2 plus over there. But we do have 2 NO3 over there. Cross those off. And what you have left that's the net equation.
So the net ionic equation is just the one that becomes inside of
Yeah, it just shows the ion that this solid was formed from. You could say it that way, or you could say you're canceling what's the same on both sides. Either way, you get the net ionic equation. One more vocabulary word. Spectator ions. The whole point of doing a precipitation reaction is to get this. So we're really focused on this stuff here. These things that I crossed off are the spectator ions. Potassium and nitrate are spectator ions here. And notice I could use something other than K and something other than NO3 just as long as they would still be soluble. Because the whole point was to get the PbCO3. So these are spectators in the sense that we kind of don't care what happens to them. Our whole point was to make this solid. So that's why the word spectator is used. Where do we start? We start by making sure the reactants are soluble. K2SO4 is soluble. It's all right. Aqueous here. Calcium iodide is soluble. So we have the possibility of a precipitation reaction. What goes over here? Two of those and two of those, so I need a 2 here. Now it's calcium and sulfate. Ca is 2 plus, SO4 is 2 minus. So that's balanced the way it is. That's balanced. And then there's one of these and one of these, so we're good. AI, is that soluble?
Soluble. And so is the other one.
Calcium sulfate. Sulfate, anything sulfate is soluble except for these 3 things.
So it's no reaction.
Everything sulfate is soluble except for,
Will we get the soluble and insoluble charts, or will we have to memorize it?
yes, I'll give you both of those. That's why I made this PowerPoint. Whichever one of these you like better, you can learn. I like this one because everything's split out like this. Actually, my neat summary there is probably the best one. I got a picture of that. But I'll give you those charts.
Okay.
Calcium sulfate.
About what we use as well.
Huh?
That was aqueous as well, right?
Anything sulfate is soluble except for these 3.
So it is soluble because it's calcium. Right?
Yes.
So it's no reaction.
Yeah, that's a no reaction one. I had to get all the way down to calcium sulfate is partially soluble. Well, I better add those even though they're not in this chart. I better have that cut off. All right, I'll fix that chart. But let's go by this.
So it is a salt?
Yeah.
Okay.
I think these are partially soluble. Or maybe it's these 2. No, these 2 are calcium's partially soluble. I'm sure that's why they're putting it in there. But let's just put it in here. We also had, what else did we have the chart now? SR. Silver sulfate. I'll fix these charts. Have PB in there. This is kind of a limited list. Most textbooks just pick a few very common ones. So I'll fix the charts, but let's go from there. Okay, so we're going to assume calcium sulfate is soluble, insoluble. It's actually partially soluble, but this will, I won't go into it. Okay, so the ionic equation. There's two K's, aqueous plus SO4, 2 minus aqueous.
Does it matter what order, like, where?
I could have written this first.
Okay.
I could swap those. There's no rhyme or reason to that, just as long as they're both there. And when I do this, I think the easiest thing to do is just split them out. So there's the ionic equation. The net ionic equation is we'll cross off the 2K, and we will cross off the 2I, and we're left with net ionic equation. You guys okay with this?
This might be a very dumb question. How do we know what these charges? Like our other charges is compensation for SO.
You mean all of these charges?
Yeah. And like our level of program.
This is going back to test one information. All of these are going to be +1, all of these will be +2. All of these will be -3, all of these will be -2, all of these will be -1. And then stuff like this, the polyatomic ions, those are in that chart.
Okay.
I included it in the test 2 PowerPoint just because I thought you'd want to see it again.
Okay.
Sulfate is right here, 2 negative. What else do we have?
That makes sense. So how come for like the potassium you pulled the 2 out in front, but for the SO4 you didn't pull the 4 out in front? Is that just because it's
You mean this out in front, the number here?
the second reactant?
This one? So this is, the SO4 ion is 2 negative, the calcium is 2 positive. So
Yeah, I agree. Sorry, I don't think for it's like the ionic equation, you pulled the 2 out in front. How come you wouldn't pull the 4 out in front as well? Is that because it only goes with oxygen?
this means we have calcium and we have the SO4 is weird. But there's only one of them here. There's only one SO4. This goes together as one thing. So this is together as one thing. There are 4 oxygens here, and there are 4 oxygens here, so I don't need 4 out front.
I was just asking in the ionic equation one, like the.
Are you saying why is there not a 4 here?
Yeah, but when it's not combined with calcium.
Because it's a solid, I'm never gonna split it out as this. But if I did split it out, I'd split it out like that, and there would be one of these and one of these. The S and the 4 O's stay together as one thing, because it's a polyatomic. But I didn't split them out, because it's soluble, it's solid.
Yeah, I was just talking about before it's being combined, like at the very beginning, but it's okay.
Okay. I'm not sure I understood your question. Ask me before you leave if I didn't answer it.
Okay. I have two questions.
Okay.
So, what is the difference between the two being like after the K and then having it in front? Like, so like the molecular equation, it's K2, and then the ionic, or ionic, you change it to 2.
If I split this into all its ions, I get K plus, and SO4 elements. Because there's two Ks here. But instead of writing it like that, K plus plus K plus, I'm writing it as 2 plus,
Okay.
2K plus.
And then also, so the ionic equation going to, like when you're splitting everything up, why did you split the 2Ki, but not the CaSO on the right side?
Because it's a solid.
Okay.
It doesn't split into ions.
Oh, okay.
These all dissolve, aqueous, aqueous, aqueous.
Okay.
So in some sense, this is a superior way to write it because this doesn't really exist. CaI2 doesn't really exist. It exists as Ca2 plus I minus and I minus. So that's what this is expressing.
All right, thank you.
You sure?
Yeah, I got you.
Any other questions? I'll probably have to give you guys some balancing equations stuff. So I'm going to, let's see if I can explain. See if I can explain the polarity. In a reasonable amount of time. Bond polarity. That's 23 and 24. periodic table, the one that I use, and that I give you for test. So look at the periodic table and look at the number in the bottom right corner. You see this number? That number at the bottom there is an expression of its electronegativity. And I'll bring up. I lost it again. Electronegativity and bond polarity. And I only came up here for this. So if you look in the section in 5.2, it says predict 5.2 electronegativity. Just look in the first sentence where it says the ability of an atom to attract electrons to itself in a chemical bond. You should say a covalent bond. That's the definition of electronegativity. I always say that. So if you're looking at the periodic table, electronegativities are there for you to see. Boron is 2.0, carbon is 2.5, nitrogen is 3.0. Oxygen is 3.5, fluorine is 4.0, what else should I put here? Sulfur, phosphorus, chlorine, sulfur, phosphorus. Putting these here for me so I can use them in a second. Chlorine is 3.0. It's 2.8. Okay, so the electronegativity of carbon is 2.5. The electronegativity of sulfur is 2.5. The electronegativity of oxygen is 3.5. And that's listed on that periodic table, so you don't have to memorize these. Hydrogen is 2.1. Here's a molecule. If I wanted it to be a Lewis structure, I'd put these pairs on there, which I guess I'll put. Okay, here's the point. Table 5.1. I'll put this in the PowerPoint. So if you follow these rules, what you look at is the electronegativity difference. So if I look at carbon to carbon, I'm looking at this bond. Carbon is 2.5. So I'm comparing a bond between two carbon atoms. I take that number, I do the subtraction, I take the absolute value, and it's 0. That's in this range, that means it's a non-polar bond. I'll tell you what I mean by polar. If I compare carbon and hydrogen, carbon is 2.5, hydrogen is 2.1. I'm still in this range of non-polar. So all of these bonds, carbon to hydrogen and carbon to carbon, are all non-polar bonds. Now let's do carbon and oxygen. Carbon is 2.5, oxygen is 3.5. Now I'm in this range, and what that's telling you is this is a polar bond. That's polar. What I mean by polar, question?
Yeah, I was just asking, it says that non-polar is 0.4, but it also says polar is 0.4. So, how do you?
Yeah, I know what you're saying. Non-inclusive. Okay, so what I mean here by polar, notice that oxygen has a larger number for its electronegativity. That means it has a tendency to pull those electrons towards itself more strongly than carbon does. So these electrons in this bond are really mostly being pulled towards the right side more than they are to the left side. It's sort of a tug of war for those electrons, and they're not shared evenly. Oxygen kind of pulls them towards itself. I'm trying to do that with this wedge here. So what that means is the right side here is slightly negative, and the left side here is slightly positive. We usually do that with this lowercase delta, lowercase Greek delta. You can also say that there is a dipole here. So if I don't use that word, make sure you know what it means. But this is a dipole. Dipole meaning it's got two poles, a negative pole and a positive pole. So this is polar, it has a dipole. Slightly negative on the oxygen side, slightly positive on the carbon side. So it is polar. Another thing we do to represent a dipole is we draw an arrow. The pointy end of the arrow goes to the negative side, and you just put, what I'm drawing here is this, you can't see it. And you put kind of a plus symbol on the left side, so dipole. So that's a polar bond. Oxygen to hydrogen. Oxygen is 3.5. Hydrogen is 2.1. So what do we get here? 1.4. 1.4. So that's still in here. So this is also a polar bond. This is. Oxygen stronger than hydrogen. Slightly positive there, slightly negative there, slightly positive there. The lowercase delta is just means slightly, meaning that's a full plus charge. This is a partial plus charge, less than the overall charge. This is a partial negative charge, not a full negative charge. That's polar. The trick to polarity, so you need to be able to do this. You need this. I don't mind giving it to you for a test, but those pieces of information, plus these numbers on the periodic table, you can figure out polarity.
Wait, what was the arrow with the like line there? What is that? Is that what it
It's just a way to represent a dipole.
is?
And the pointy end points towards the negative side, and the one that kind of has a plus symbol, kind of looks like a plus symbol, goes on the positive side. I could have drawn one here too.
Okay. It's not necessary though, or is it?
Just recognize what it is. That's very, very common nomenclature to represent a dipole that way.
So
Okay.
in that example, the oxygen is the more electronegative.
Yeah. This is more electronegative than this. This is more electronegative than this. So this molecule has some polarity on it. It's got polar bonds. The one twist with polarity is there's bond polarity, which we just talked about. And there's molecular polarity. To decide molecular polarity, first of all, polarity of a molecule comes from polarity of bonds. Maybe I want to leave that. If there are no polar bonds in a molecule, then the overall molecule can't be polar. But if there are some polar bonds, let's do C and carbon. Fluorine is the most electronegative atom. I could ask, are these polar bonds? Carbon is 2.5, fluorine is 4. So that makes it's 1.5. I can't do math in front of you. So these are very polar bonds. But the trick here is, what is the molecular shape here? This is tetrahedral, good. So you picture that tetrahedral shape, and if every one of these, I'll do this to indicate that. Four polar bonds. The next question is the molecule polar? If it's perfectly symmetrical like this, all those dipoles cancel each other, and this molecule is not polar. That's the twist with polarity. You have to think about the shape and decide whether it's perfectly symmetrical. If I did this, it's still tetrahedral, but look at the dipoles. If you think about the dipoles, it's not symmetrical anymore. This will be polar. That's the one twist in polarity. Bond polarity is very straightforward. Molecular polarity, you've got to think about the overall shape of the molecule and whether it's symmetrical, or at least around some central point. Same here. Difference between carbon and oxygen will make this polar. But that's a linear molecule. If I ask you what's the shape here, you would say linear. Those perfectly diametrically oppose each other. They cancel each other out. This is a non-polar molecule. But if I had sulfur. Yeah. Sulfur is 2.5 and carbon is 2.5. So there's no dipole there. So we have a polar bond here, not a polar bond here. With respect to this arrow, it's not symmetrical anymore, so that will be a polar molecule. Because it's not symmetrical with respect to the dipole. That's the one twist with polarity. Polarity is very easy. When you get to molecular polarity, you have to start thinking about the shape and its symmetry. There is a way to add these as if they were vectors. Anybody ever do vector addition in a physics class somewhere? But that's the idea. The way I say it is symmetrical or not. But there is a way to add these to find out what the overall dipole would be. And since this is tetrahedral, I can't really draw it, but there is an overall dipole that's something like that for this. And this one's overall dipole would be something like that. Because there's only one, so it's going to be. So if it's not symmetrical with respect to the dipoles, it will be a polar molecule. If it is symmetrical with respect to the dipoles, it's non-polar. And if there are no polar bonds at all, then there can't be a polar molecule. Some books add in a twist. They say if there is only one polar bond, then it will be a polar molecule, which is generally true, but it depends on how big the molecule is. But I think you talked about that in 1212. So if there's only one polar bond, it'll be a polar molecule because there's not another vector there's not another dipole to cancel it. So some books mention that. No polar bonds, not a polar molecule. One polar bond, it is a polar molecule. More than one, you have to think about the shape and decide whether it's symmetrical or not. I don't have questions up over molecular polarity yet, because I was waiting until we did molecular shape. But now that we have, we'll talk about that. And we have a lab on that we'll do. So now that we've done molecular shape, we can do lab, the one we skipped. All right, I'll stop there. See.
Do you know when this lab will be?
I think we'll do it next Wednesday, but I'll give an announcement. Fall break is Monday, right?
Monday and Tuesday.
Monday and Tuesday. Oh, yeah. I want to go and just take pictures and put it in a Word document and upload it. But I'll put instructions online on how to do it. Because you have to copy and paste and put it in the Word document, just so all your stuff is in one place. And then I'll give you somewhere to upload it.